Podcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Thanks for making it to the webinar today. We've got a pretty good one. I know I've attended this one for the I2SL webinar that Kishore did, and it's really insightful, and I think everybody's going to get a lot out of it. First things first, if anybody's got anything or any issues, just text in the chat box on the right hand part of the screen there. It's the only way that you're going to be able to make your voice heard, and that's where we're going to be asking questions as well. So at the end of this session, we've got about 15 minutes for asking questions, and I'll be taking note of all those questions and then putting those to Kishore here. So air change rate or HVAC configuration, which makes labs safe. Today we've got Dr. Kishore Kankari, PhD, who is the president of Ansight LLC, a specialist in computational fluid dynamics. He works closely with his clients to provide engineering insights and optimize design solutions using analytical techniques. Kishore has several years of experience in providing consulting services and insights through analysis to a wide variety of engineering problems involving fluid flow, heat transfer, mass transfer, and other similar engineering processes. Dr. Kankari has developed a patented technology of a wind band design of exhaust fan assembly systems. He has developed several easy-to-use analytical software tools, which are regularly used by design engineers in a variety of companies, including those in the critical facility and automotive industries. A noted expert in his field, he has a PhD in CFD from the University of Minnesota and has been regularly publishing in technical journals and trade magazines. Dr. Kankari is an eloquent speaker and has made several presentations worldwide on topics related to design and optimization of HVAC systems at various technical conferences and professional meetings. ASHRAE recognized him as a distinguished lecturer. Dr. Kankari is ASHRAE Fellow and recipient of the ASHRAE Distinguished and Exceptional Service Award. He's currently leading the ASHRAE Multitask Group on air change rates and I2SL Technical Group on ventilation effectiveness for laboratories. He is past president of the Detroit ASHRAE chapter, past chair of ASHRAE Technical Committee TC 9.11 Clean Spaces, and past chair of the ASHRAE Research Administration Committee. He is a member of the ASHRAE Environmental Health Committee and voting member of ASHRAE Technology Council. He serves on Industry Advisory Board for Architectural Engineering Discipline of Lawrence Technology University. So a great speaker, and I'll pass it over to you, Kishore, for your presentation.
Thank you so much. Thanks for inviting me to speak here. I'm quite excited. This is my passion, as you know, and what I'm going to talk today is what's the role of air change rates really on dilution of lab ventilation systems, if you will, and then what's the role of HVAC configuration, meaning how many exhaust grills we have, where we place them, what kind of diffusers we place, and so forth. So you can say it's the competition between the dilution versus ventilation effectiveness. And so with further delay, let me start with purpose of lab ventilation system. I've been practicing this for a long time, about 30 years, and I always like to start with why are we ventilating our buildings? What's the purpose? So our purpose here for lab is to minimize hazard due to airborne contaminants. We have to keep that in mind, the airborne contaminant, by lowering the concentration with dilution. So we are trying to reduce the exposure by dilution method of airborne contaminants, mainly gaseous contaminants. So how we do that? We bring the concentration levels to certain acceptable level, and whatever that is, whatever hygienist tells us or NIOSH tells us, we use that. And then we try to achieve as much as possible uniform concentration. And remember, our critical zone in the lab, so far the safety of the occupants is concerned, is the breathing zone, which is, you can say, 4 to 6 feet height or 5 feet height from the finished floor. And while we are doing this, we should do this in an effective manner. So what I mean by that is, see, we spend several $100,000 bringing the air to the lab space. Is that air doing its job? Is it short circuiting and taking the path of least resistance, getting out of the lab without doing the dilution? Or is it just staying there for a long time, like sometimes unexpected guest stays there, you know? So is it staying there for a long time and not leaving the space? So that's what I mean by effective manner. The key here is, even though this sounds very good, we really don't have any good measures to quantify this. Are we achieving the purpose of lab ventilation? So let's go to the basics here. What is air changes per hour? So you take the supplier flow rate, if you're doing in CFM, multiplied by 60. And remember, the volume of the lab comes into picture, the volume of the lab. So if somebody says use 6 air changes for your lab, the design engineers take that 6 air changes, multiplies by the floor area and height of the space, and then finds, oh, what kind of air handler I need for this building. So when design engineers get that number, they don't think whether I need 6, 8, or 4 or 3 air changes. That's what the codes and design guidelines specify, and we get that. So are those 6 enough? Are those 4 enough? So generally what I see around is more is better. If the 6, we are running our labs at 10 air changes because 10 is better than 6. Really? Let's try to find that out. So here are some popular notions around, and what I heard from my colleagues and people I come across. High ACH can create well-mixed conditions. By the way, that air change rate equations and the dilution equations, they assume the space is well mixed. It's like you're putting a creamer in your coffee cup and stirring it well. So it's an homogeneous mixture. It's not like that. I mean, no space in the world is well mixed, no matter what you travel. It's a small, very simple to very complex process. Another thing, people think high ACH can create uniform concentration levels. Again, that goes to that mindset of well mixed, that if I well mixed, then uniformly I can create the similar concentration. High ACH can reduce chemical exposure risks. Again, more is better. If I put more air, more dilution, my exposure risk will be lower. And then, not related to ACH really, but there is a notion that if I stick a sensor in my exhaust duct and I can monitor the environment, I'm saying because I have a sensor, but your sensor is in the exhaust duct. We don't live in exhaust duct. Our nose is not in the exhaust duct. We live in the lab, and our critical zone is 4 to 6 feet high. Well, what are the factors that control the spread of contaminants in the space? Of course, the first thing is supplier flow rate, or you can call it air changes per hour. They are not the same thing, but they can have the same dilution effect, correct? The higher the supplier flow rate, higher air changes, it will give you a higher dilution. By the way, only supplier flow rates controls your dilution. Air change rates not. Air change rate are required to control your purge and ramp up phase, and I will come to that. Rate of contaminant generation. What type of contaminants are there? Where they are located? What is the rate of their generation or evaporation or something like that? Location and number and type of supply diffusers you are using. location and number of general exhaust you have in the space. If it is a fume hood dominated, then how many fume hoods, what is their capacity, where they are located, and then, of course, where are the heat sources, where people are working in the lab space, and whether they are moving around and so forth. So, and then finally the layout of the facility, how your furniture is laid out, where you are laying out your supply, what type of diffusers, and where your returns are. So these are different factors that can affect the spread of contaminants. What I'm going to concentrate today on two parameters: the supplier flow rate or air change rate, and location and number of general exhausts. So, as I said, it's hard to quantify, and computational fluid dynamics science helps us to kind of put a microscope on my lab space and look into the detail, where my concentrations are, where they are moving, how they are moving, why they are moving, and how can I compare design A versus design B versus design C? I mean, all these designers and engineers can come that their lab is the safest lab. How can we quantify? So I developed what I call the spread index and push time, and I will talk about that. So here is the simple CFD model. So don't look at it as, hey, my lab doesn't look like that, or I have 5 fume hoods in the lab. Okay, those are all valid configuration. Just to prove my point, I took a simple configuration. Think this as a chemistry lab. There are benches here. There are 3 researchers working here, and assume that somebody spilled a chemical here. This guy, person 2, did something and spill it on the bench top. So for ventilation is concerned, we have 3 4-way diffusers in the lab over these working spaces. And then we have 2 exhaust grills, as you can see here. Again, there is a door undercut, there is a door here. So a simple configuration because we want to prove our point here, okay. Now, this is about 660 square feet lab. It's working at slightly negative pressure. That's why there's 100 CFM leakage bypass through the door. It's under isothermal conditions. Again, you may say, oh, what happens to the heat dominated lab? Well, it can be different. The buoyancy can make a difference. And then your priorities will be different. If it's a heat dominated lab, you're more concerned about the thermal comfort of the occupants along with the safety of the occupants. So that's a completely different ballgame there. Hypothetical release is 7 ml per second. Again, this is hypothetical. And let's say the whole liquid is evaporated in 12 minutes, and we will run this analysis for 60 minutes. And what we are going to do, we will run the exactly same lab for 4, 6, 8, and 10 air changes and see what happens. And then I will show you 3 different configurations here. So first thing, airflow patterns in the space with what is going on with COVID-19 now and all over the world. And there are so many things in the newspaper and LinkedIn and whatnot. Airflow pattern is the most important factor, is the primary carrier of heat, moisture, and contaminant. So how air moves and what flow path air takes, it impacts the flow path of airborne contaminants. So looking at this, what you see, it is not a simple airflow pattern. It's not something what you draw on your 2-dimensional drawings and beautiful arrows to show where the air is going. Those arrows simply convey your intent of air motion. Air doesn't behave the way you intend it to behave. I mean, air has its own brain, and you can see here when the air comes for this 4-way diffuser, some of it is kind of escaping, and then it's forming a large recirculation zone here, and so forth. So I'm just showing a different plane, but if you look at it in a 3-dimension, we can't even imagine what's going on. It will be full of colorful spaghetti, if you will. Now, this is the key question. You take the snapshot in a time, which I took after 12 minutes when my release of contaminant reaches its peak. And if I look at the air changes here, what you see, the first thing, the notion that higher air changes can create uniform concentration is a myth. It's not true at all. So no matter what you do, you will not be able to create uniform concentration in the space. So what you are seeing here, certainly where air changes come into picture and help us in dilution, no brainer there. More air for the same contaminant generation rate, you will see more blue color here. By the way, this is a contour plot and it's showing the concentration in ppmv, and I capped it at 25 ppm. And so throughout my concentration, I'm going to cap it at 25 ppm. It's arbitrary. Assume 25 ppm is our acceptable concentration level. Okay, and again, that's arbitrary. You can have 5 ppm, or 10 or 50, whatever. So what we see here is, again, when you have low air changes, the color of red here is spread quite highly compared to the thin air changes. So as you increase the air changes, that extent of that red color kind of reduces, and it's kind of logical and understandable. So if we can now animate this and look how it is spreading with time, from the time of release till it's fully evaporates, and check here, this color is always, this spread is always smaller compared to this. And this room with 10 air changes is purging much faster than the 4 air changes. When you will get full blue color, we are still at the yellow or green color here. So air change rates affect the rate of purge. That's a very important thing to note. Supply flow rate directly affects the dilution. You can see now this is completely blue and we still have the shades of green and light blue there. Now, what you're seeing here is the cloud of 25 ppm. What it is showing, everything under this cloud is at or about 25 parts per million. Now, this gives you a three-dimensional picture where all that contaminant is going. What portion of my lab is not at safe level, assuming 25 ppm and below is the safe level. So what you are seeing here is, as you increase the air change rate, the volume of that blob occupying the room space decreases. So here it is 33%, 27% in 6, 8%, 19% in 8 ACH, and 11%. So there's significant reduction when you go from 4 to 10. And this reduction, you will see, gradually diminishes. So you may not see a big difference between 8 and 10. We can animate this to show actual propagation of this high concentration zone in the lab space. This is not possible to visualize by any other means than computational fluid dynamics. I mean, that's the beauty of CFD. This is a science. This is based on the conservation mass, momentum, and other equations. You see, again, if you watch that, this takes a long time to purge. And when you have the contaminants kind of trapped between the benches, that is the last spot to clean. Air cannot reach effectively between those spaces, between those cabinets, or between the beams if you have. Those will be the last spaces to purge. So more open cabinetry you have, it's better. If you create a lot of compartments and zones which are trapped, contaminants go there and they will be last to remove. Again, you see, this has already gone out from there, and this is still going through that. Now, let's understand the chemical exposure here. So just the absolute concentration is not important. How long a person is exposed to that concentration. So what you're seeing on this is time versus the concentration. And what I did is I placed the sensors in front of their noses here. So each sensor is in front of their face. So I can actually with time monitor the concentration. What is interesting here is person 3, who is away from the source from the person 2, shows highest concentration exposure. And then next comes the person 2, and then comes the person 1 here, who is kind of in this position here. So this air is trained to move along this side, as you saw in the animations there. If we convert that into the exposure, that's the area under that curve, or ppm minute kind of unit, you will see that person 2 has much higher level of exposure, who is not even close to the source of release. And again, I want to make a reference to what's going on in this pandemic, and not related to droplet, but to aerosol. If somebody is asymptomatic and is breathing the germs out, maybe the person sitting next to that person may not be the one who gets the higher exposure, maybe someone else, and that will depend on what kind of airflow patterns you have. So you can see that person 2 is the next one, and person 1, of course, has the least exposure. I plotted this, the exhaust duct concentration, just for your reference here. And if you're monitoring the safety of your lab using the sensor in the exhaust duct, you will over-predict for few occupants, and you will under-predict. So under-prediction is most concerned here. If you think everyone is safe using this dotted curve, that's not true. Again, I'm not against putting the sensor in exhaust duct. That can act as a smoke detector. If there is something, if there is a spill, it will trigger the alarm. But it's not necessarily, it's a detector. It's not a monitoring device. So we have to keep that in mind. Now, if we look at 4, 6, 8, and 10 air changes, very interesting thing you see here. For person 1, you can see this red color is for 4 air changes. I thought that red will be always on the top and the blue will be always at the bottom. That doesn't happen like that. You see, 10 air changes, they are higher. The concentration is higher than the 4 air changes here. In fact, 8 is even higher, similarly at high peak level there. Where you really see the effect of air change rate, as I said, during the purge cycle, where you reach the peak and now you are purging the lab, cleaning the lab, you will see that higher the air change rates, it purges faster than the lower air change rate. So definitely they stack up very well in the purge cycle, but not when the active generation is there. So you can take this for the fugitive emissions, or other gas leaks or something like that. This is an accidental spill, and what it also tells you, like how long you should take to take the people out from the lab when there is an accidental spill. What kind of exposure they will get if they are delayed to evacuate the lab, correct? So you will see, if you are going to take 5 to 10 minutes to get all the people out from the lab, well, at higher air changes, you will expose them to higher level of concentration. So for person 2, similar story here. No, this is the exposure for person 1, sorry. So what you see here, again, higher exposure at higher air change rate. So high air change rate will not always give you the lower exposure. This is for person 2, more or less same story. You can see these peaks are popping up here and there, and this is the 10 air change rate. So if we look at now the exposure for this person 2, who is close to that spill, of course the 4 is highest here, but it is not stacking up in this order. 10 is next one. I was expecting the 6 and 8 and then 10, 10 is not the lowest one. Similarly, for person 3, you can see the higher air change rates are giving me higher concentration. And if you look at now the how they stack up during the release phase, when there is the active release of contaminant in the lab, higher air changes are giving me higher exposure. Where they are stacking up probably here is when probably there is nobody in the lab. By 10 minutes or 15 minutes, people are already leaving the lab because of the spill. They left this empty lab. Really, exposure is secondary. I don't care what the exposure level in the empty lab is. There's nobody, no occupant there. What it will help you, how soon you want people to get back to their work in the lab, higher the air change rates, you will purge the lab quickly. Okay. Here is the ventilation effectiveness measure I developed. So our goal is to minimize this blob. Remember, this blob is the cloud under which the room is not at acceptable level of concentration. So we can quantify this. We can take the volume of this blob and divide it by the volume of the room. As I told you, this is only possible with CFD. You cannot do this. You will need, even if you bring million sensors in your lab, you will not be able to quantify that. So, and remember, this is a volumetric phenomenon. It's not a one-point detection like an exhaust, or it's not just the breathing zone thing. It is in the entire lab how it is spreading. So, and then if you are more concerned about the breathing zone, we can do the same calculation for the breathing zone. So our target in this example is 25 ppm. So if your target concentration is 5 ppm, you can calculate the spread index for 5 ppm. You can calculate the spread index for different chemicals you are using in the lab. You can use different levels of acceptance and find what is happening. So it's not just one spread index. Spread index can depend on type of chemical and what is your target concentration for that vapor in the lab. Okay, so it's not just one. I mean, you can do this analysis for various concepts and of course at the breathing zone. The purge time is the time it takes to reduce, to bring the lab concentration at acceptable level. Remember, when your spread index is 0, it does not mean your lab is clean. What it is simply telling you, your lab concentration or the contaminant concentration in your labs are at safe level. It doesn't mean they are 0, they are at safe level. And that safe level can be different for different chemicals, for different labs, different applications, and so forth. And our goal here, remember, is to minimize this SI to 0 as quickly as possible. So that's where the purge time comes in. Now, if you plot this spread index with time, you will see the spread index goes up, and as I showed you, it's about 33% of the lab volume. The spread index is 0.33 at its peak, and then it drops down pretty quickly. Now, what is interesting here is, if you use 6 air changes instead of 4, you will spread it much faster. Similarly, in this, during the early stages of release, the air change rates may hurt you than help you. Where air change rates will help you when you are in the purge cycle, and you see they are stacking up very well. Now, if you look at the purge time it takes, so 4 air changes will take about 20 minutes to purge. For 6, it's about 7.5 minutes. But for 8 and 10, it's almost similar. It's about 5 minutes. So why, if your goal is to purge the lab, for example, in the demand control ventilation, why would you design your air handler for 10 air changes when there is little difference between how long it takes for 8 and 10 air changes? So it shows that you start getting the diminishing returns as you start increasing the air change rate. And I'm not the first one to tell you this, you already know that. So what we learned from this first exercise, high air changes do not necessarily create well-mixed uniform condition. Exposure level depends on the location of occupants, where they are located. High air changes do not ensure low exposure for all occupants. Remember that. I mean, you can reach that peak pretty quickly and give that high exposure dose to some occupants. Higher change rates do not necessarily purge the rooms more effectively than lower air changes. Now, what I mean, when you have a trapped volumes of the gases, then it doesn't matter whether high or low, it will take its time to clean that space. Impact of high ACH is realized only during the decay phase. Okay, that's what I said. Now let's look at the configuration here, and let me do a little time check here. Okay, we are good. So let's think about this lab, exactly same lab. We are running at 6 air changes. The only difference we are going to make is add one more exhaust grill. And I was talking to my design engineer, a friend, said, hey, tell me approximate cost. I said $500 installed for one more exhaust grill. Now, again, I want to make a reference to COVID situation here as we are reopening and getting into the spaces. Where the exhaust grills are and how many exhaust grills, that will make a big difference. And I will show it to you shortly. So that's the only difference. One has 2 exhaust grills, another has 3 exhaust grills. Exactly identical generation rate, same air changes. You see a difference here when I look at that 5 feet. You see the extent of sprayed here at 12 minutes. And compared to this, as soon as I add that, I'm creating an additional path for contaminants to leave the room. I'm creating the path of least resistance for contaminants to leave the room. As I said, I don't want them to sit there, wander around, take their own time. No, I'm showing them the door right away, get out of here. And if you create that extra grill there, place extra grill, you see the difference here. Look at the animation here and watch that red zone. You see that red zone is mostly now in the middle aisle where the spill was. Versus you look, this guy's face is almost immersed in that one. Versus this one here, and much difference you see between these two cases. Remember, they will purge at the same rate because I'm not changing the air changes. They are at the 6 air changes. So the only thing that affects your purge time is the air changes, not where you place your exhaust grills and so forth. This is a quantifying thing. If you think this as a sprayed index, you can see it is 0.27 or 27% of the lab is occupied by unacceptable levels of contaminant versus 16% here. It's a big difference, adding just one more exhaust grill. Let's look at the breathing zone. If you say, I don't care what's happening near the ceiling, and I don't blame you, you are right in your thinking. If that is the case, even there, I see a big difference between 5.3 and 3.4%. As I mentioned to you before, this is where the power of computational fluid dynamics comes into picture. Again, we need to now come out of our 100-year-old uniform mixing dilution methodology mindset and adapt to this new technology, new techniques to design. Remember, again, this guy's face is completely immersed in that dirty cloud, if you will. We took that guy out from here and it reduced to that. Look at the animation here. And this is very compelling to see that just adding that $500 grill helped me to contain that blob, red blob, in a narrower space than just with the 2 grills here. Chemical exposure analysis, and I'm going to just go quickly through this. The dotted line is 2 grill, solid line is 3 grills, and 3 grills is always below the dotted line. It's a significant difference in the long-term exposure. Same thing here. Again, notice during short duration, 3 grills for 2% is going above the two grill section here, because now you are studying that contaminant in that zone only. So this person 2 in the short term may get higher exposure, but long term it's much. And look at the person 3. It's a significant reduction for person 3 in the exposure level. So look at the ventilation effectiveness, the sprayed index. Again, significant reduction in the sprayed index. Water, we just looked at the number, 27% to 16% here. And this is the first time. Again, 3 grills are taking 720 seconds versus 2 grills which are taking 420. Again, 3 grills, there are trap volumes in there. And that's where that at tail end, you will see the difference here. Now, people say, well, more is always better. If 3 make that difference, what about 6? We can put 6 grills, move the supply diffusers at the center. Let's look at it, what is happening. It's, it's doing it worse. It's making it worse, okay? You should not draw the contaminants where the occupants are. Very simple principle. Again, I want to make reference to COVID situation. We should not pull the contaminants towards the people. We should pull it away from the occupants. And so when you added 3 more on this side, so there are 6 grills here, you see this has spread even more. Look at the animation. It takes some time to pick up because we have the ready exhaust there. But once it starts building up, it starts spreading more because that pool of contaminants saying, hey, there is one more exit for me to get out from there. But whatever that configuration is, that's not allowing that ready path for the contaminants to get out. Now, this is not just a combination of 3 versus 6. It is how the lab is laid out, where the diffusers are, what kind of diffusers they are, and there are a variety of other configurations and factors. So you can see here again that red blob, it has spread quite a bit in the lab, compared 16% to 23% here. What about breathing zone? It's even worse, from 3% to 16%. And look at their faces are completely immersed in that red blob compared to here. Again, this should be done at a design stage, if possible, at a schematic level. When you decide your furniture, when you decide what kind of chemicals will be used, what kind of lab it is, what are the how are you using the lab and so forth. So what is your practice? And put that together to find the optimum optimum air change rates and optimum configuration for the lab. Again, look at this animation here. You can see how it is getting retaining near that central aisle versus here it is spreading in most of the lab zone there. So chemical exposure analysis completely reversed now by a dotted line, which is the three grills, and solid line is 6 grills. 6 grills are making it worse because we are pulling the contaminants towards the occupants. Same thing with person 2, same thing with person 3. Again, you may ask, well, the location is not fixed. Person 3 can be anywhere. Yeah, this is just the, instead of having nothing, at least this gives you a starting point to understand. Remember that spread index is giving you a fair comparison between design A versus B versus C versus D. Which one is the good? Which one is the best? And you don't know. You can, there may be just hand waving, oh, maybe like this, maybe like that. Oh, because this is good. And intuitively you will think, oh, if 3 is good, then 6 must be better or best. And that's not the case unless you do that analysis. So ventilation effectiveness, again, the same story here. Unfortunately, you can see 6 grills spread it more. So to summarize what we have learned today, high air changes alone cannot make labs safe. Don't just simply increase the air changes. Don't just think that 10 is better than 6. It may not be, depending on the purpose of your lab and what you're doing. Whether it's an accidental spill or is it a fugitive emission, is it a gas leak, or what it is and what you're trying to achieve. So the blanket statement saying that higher air changes will always make my lab safe is not true. Okay. Uh, Configuration matters. As I showed it to you, location and number of exhaust grills matter. Uh, Place exhaust grills away from the occupants as much as possible. Don't try to pull the contaminants where the occupants are. I was designing the smoke, evaluating the smoke exhaust system, and generally architects don't like to see the dirty grills in their space. I don't blame them. They're not very pretty looking. So they just put the linear diffuser, linear grills on the perimeter. And this is like 3-story space, and there's a balcony and circulation place. And they pull the smoke towards the people where the path they will take when there is the smoke in there, and that's where they will find their stairwell. And if you do that simply for aesthetic point of view, you're putting people at risk, their health at risk. So when you put that at the center, because smoke rises up and it's hard, it readily gets out of the space without spreading. So placement and number of exhaust grills is quite important. Just following the codes and standards is not enough. This is my favorite. Nowadays, I'm passionate about this. Well, you talk to engineer or contractor and say, oh, we are following the code. We are following the building code. We are following the standards. Who is writing the code? Who is writing the standard? You and me are writing the standard. And how we are developing our code? It's simply by yea or nay. 10 people sit there. Who are in favor of 6, raise your hand. Who are in favor of 10, raise your hand. And whoever gets the majority vote, that goes in the code. Is that a very scientific way? And then we always forget the codes and standards are minimum requirement. Show me one code, show me one standard in the world that tells you if you follow these instructions, if you follow these guidelines, people will be safe. Based on the experienced engineers and professionals, they get to, I don't blame them, don't take me wrong. I mean, we should have codes, we should have standards, but don't take codes and standards as the final word. It's not. And they are not necessarily designed to make the labs or spaces safe, healthy, and productive. That is our responsibility. If you have a passion and compassion for the people who are working in your lab, you need to take that extra step and extra due diligence to make sure that whatever I'm designing is going to safeguard the lab and will meet the purpose of the ventilation. And that's where CFD comes into picture. Again, I'm not trying to sell you CFD. Try to understand there are many advanced techniques and advanced design. Those days are gone. When those guys didn't have CFD, the only equation they could develop was first order dilution equation. It's not bad. It's still the first step. It's still the back of the envelope calculation. Maybe 50 years ago, it was the prime calculation, but now in today's context, it has become the back of the envelope calculation. People always ask me how much it costs to do a CFD. Well, somebody did a very good study. It said if the design costs $1, the construction will cost you $10 and operation will cost you $100. The cost of the people, their retention, their happiness, their health, their productivity is priceless. It's $1,000. So it's 1,000 times the cost of the design. And yet, in our current design practices, we can't even know what we are designing is going to work. The only time we know when we get that phone call from the owner. And I'm sure nobody wants to get that phone call. So how much CFD costs? It's 10 cents. Those 10 cents are going to give you extra due diligence, extra peace of mind, if you will. And then remember, that's the passion, that's the compassion that we are making people safe in the lab. So that, that's what my presentation is. Hope I didn't exceed my time. Oh, right on time. So I can take few questions here, Kevin.
Perfect. Thank you so much for that, Kishore. That was awesome. I guess I'm just gonna ask a quick one, maybe. You kind of identified the idea of sensors in the ductwork, and I think that's referring a little bit to the air quality monitoring systems that are out there now. Do you have any kind of recommendations for effective sensor installations then, or is it more just that it would be better that it's in the breathing zone as opposed to up high in the ductwork?
Very good question. And forgive me if I don't mean to criticize any system here. What I mean to say, when you place a sensor in a duct, which is not in your breathing zone, it is simply acting as a detector. And I'm sure if you talk to those vendors and ask them why you're putting it in the exhaust duct, their answer will be, this is a detector. This is not a monitor. Monitored not definitely for the health and safety of the people. So as you said, we need to put the sensor in the breathing zone. But that is, again, the sensor location can be optimized using CFD. Correct. So you can put it in a breathing zone, but find a critical location, or maybe not just one, but put three and take the average of that, and then let your system work in tandem with what you have in the exhaust duct. So you will clearly see the difference. And there are people who are putting the tracer gas and kind of measuring the concentration in a plane. And once they put the sensor in a duct, they see a big difference. The concentration at breathing zone level is very different than in exhaust.
Yeah, that makes sense. All right, and getting into some questions from the people online. Is the supply air outdoor based, or can you use return air from spaces with the same air quality level to get the air change rates that you were identifying?
Very good question. The model was always bringing the clean air. So the supply air was at zero contaminant concentration. So it depends on what kind of scrubbing you have, correct? If you are, even think about the filters are not 100% efficient, correct? Depending on the MERV rating and the particle. We are now getting off a little bit the topic here, but even gaseous thing. So if you are kind of using the return air, then what's your dilution in the air handler is important. So yeah, that's a if you're looking at the absolute ppm level, yeah, it is important. But if you're looking at relatively between design A, B, and C, if you keep the same return air or supplier concentration of contaminants in there, you will see the same trend, because airflow patterns are not going to change whether you are bringing a fresh air or a return air. Okay.
Yep. I think that makes sense. And I think the idea is, a lot of times we try to take supply air from like the office or the administration piece of the building and transfer that over to the labs for makeup air. So it kind of goes to that idea, I think. So I guess to that idea, have you ever modeled a lab that was exhausting and really a big portion of the makeup air maybe was being pulled in from a corridor, either through kind of transfer openings or or something similar? Have you looked at that before in terms of ventilation effectiveness?
Okay. We are again, ventilation effectiveness is not a function of whether you have a makeup air, which is a transfer air from other places or not. Ventilation effectiveness is just a function of the airflow patterns in the room. Okay. So again, I didn't model that, but simply the plots I showed it to you, the blue color, let's say, will be at 5 ppm instead of 0 ppm because your supply air is not at 0 ppm. Am I answering your question, Kevin?
Yeah, for sure. I think so.
Okay.
All right. The next one is the spread index variable from different chemical contaminants.
It should be. Again, if you look at the definition of spread index, is what volume of your lab space is at an acceptable level, unacceptable level, correct? So depending on the chemical, the physical properties, the rate of evaporation, and importantly, the acceptance level, correct? So the spread index for benzene may be different than acetylene. So because just the nature of the acceptable level of those contaminants for human health and safety. So yes, that as I explained in my presentation, when you are designing your space, you should have good idea what kind of chemicals, and you do your risk analysis, what ASHRAE in the lab classification has come up, that you should do the risk analysis first before doing these things and use that risk analysis, that risk band to determine which chemicals I should use and at what rate I should release, whether it's a fugitive or accidental spill or whatnot, and use that as a basis to compute the spread index. So for a one lab, if it's a chemical lab, then depending on which chemicals and which risk level you're using, you may have 3, 4, 5, 10 different spread indexes.
Yeah, I think that makes sense. I don't know if you can maybe go to it quickly. Just a question to re-show slide 33. I forget exactly what that was, but
yeah, that's the challenge, correct? To find slide 33. Because I wish I could name, somebody was looking at the number there, but that's good. Let me go to slide. Oh, 33, just the title. I don't know. Can you give me one pointer here?
That was all that was in the question. So I'm not sure on that one, but we'll move on to the next one.
Okay.
Did you study return grills at the bottom of wells?
I did, but not up to this extent, not in a kind of a time varying fashion. I did try to play with it, and I did not find it as promising as the ceiling grill. And again, I'm not prepared to answer that question whether the low wall return or ceiling return is better. Again, it's very situation specific. For this case, it did not show much promise compared to the ceiling grill.
Yeah. And I guess, I mean, really might depend on what the prominent chemicals are in the lab, right? Whether it's something that's a lot heavier than air that might pool at the floor as opposed to something else, right?
It. Yeah, that's part of it. But the diffuser location and the supplier flow rate and throw of the diffusers and type of diffuser will make a difference. So this was promoting very high mixing because, again, I don't mean everyone's mind has this COVID on their mind. So our spaces are basically designed for mixing ventilation. So you go to all the handbooks, ASHA handbooks and theories and ADPIs and PMV and PPD and whatnot. They promote mixing because we want to mix the ventilation air with the room air as effective. But they tend to mix the contaminants also. We have to keep that in mind. So whether low wall return is always good, ceiling return is always good, whether four-way diffusers are the best versus the laminate diffuser. We don't know. It's a very situation specific because the benches you lay out will be different in one case than the other case. So it's not just the how the air moves, but the biggest portion, the biggest part in there is the obstruction to airflow. If you have a huge freezer in the middle there, it will create different airflow patterns. So
Yeah.
that will make a difference.
And I mean, just going on that, do you have any sort of recommendation, or is it kind of project specific again in terms of how many labs you would model in a new building, just considering that, you know, each lab might be different with different number of hoods, different number of benches in that?
Excellent question. My recommendation is not to model more than 2 or 3, and not even more than 1 in some cases. Why? Lesson learned. Just don't crunch the numbers and create color pictures. Some people call CFD as colorful dynamics, not even FULL, FOOL. Let's not get fooled by color pictures, correct? Learn the lesson. In my presentation, you got some high level understanding of what exhaust grill plays a role, how things move. If we understand why it happened, how we achieved the best ventilation effectiveness, use those high level principles at other spaces, unless there is a significant difference in the layout, in the chemicals, in the use, in the practice, then do another CFD analysis. But don't just try to crunch the numbers. CFD analysts love to crunch the numbers. It's like the baby when it starts crying, we put the pacifier, but we need to take that pacifier out when the baby stops crying. So CFD analysts love to produce color pictures. Yeah.
I think we've got time for maybe 1 or 2 more. And I think a few questions are kind of, you know, getting into some specifics that I think you've answered a little bit, that that getting into the weeds maybe isn't the narrative here. But placing exhaust grills away from occupants, so the 3-grill configuration shown draws the contaminants into the exit circulation path for P1 and P2. Wouldn't it be better to put them on the other side to protect the circulation path and avoiding the smoke into the exit corridors? And I think the key here too is just knowing that smoke wasn't modeled, right? This was chemicals in the air, and not necessarily smoke modeling. So I just want to make sure everybody's aware of that.
Yeah, and the corridor is not coming into picture. We have the negative pressurization, correct?
Yeah,
so we are bringing 100. Yeah. So
I think maybe the question is, you know, that it's drawing it into at least the exit path for that lab. Is that a concern, or is the idea that you're going to be exposed to it for some small amount of time, and the time it takes to walk out of the lab is probably relatively minimal?
Oh, I get it now. Excellent question. So yeah, maybe this will tell you where to place the door, or maybe that placement of that 3rd grill near the door was not right. Yeah, absolutely. We can find another place for that grill, or make just 2 grills and large enough. Don't just stick with 2x2. Make 2x4, and instead of 3, just put 2. That's a possibility, correct?
Yeah. Did you model it at all with the supply air on the far end of the?
No. I mean, there are endless possibilities.
Yes. All right, and I think maybe just the last one, and hopefully try not to go too long on this one. Like any computational model, it would have to be confirmed in an actual experiment. Is it still valuable to do the CFD analysis without experimentation?
Oh my God! Oh, this is my favorite question, and I didn't plant it. So, yeah, I always get this question: validity of CFD model. I mean, yes, it's a valid concern you have, but remember, CFD we are not the only one using CFD. The whole world is using, right from your vacuum cleaner to the heart valve and anything in between, in your car, in your shoes, in your glasses and whatnot. And the world is moving towards simulation and optimization and reducing the time to reach the market. There are several academic papers that are published in validating CFD, not just for lab, but for everywhere else. So if you have to validate with this experiment, then we defeat the purpose of doing CFD, correct? Again, don't look at CFD as the absolute final answer to your question. It is a tool. It is a simulation tool. It's better than doing nothing. You can compare A versus B versus C versus D, what I demonstrated it to you. But don't look at, oh, is this really a 10.3 ppm or 11.2 ppm? No, don't look at that. Look at where my room is getting contaminated as a because of certain layout and flow rate and ventilation effectiveness. So it's not a good use of CFD to go to the absolute minimum. Again, if you are designing the airplane, then of course Boeing has the whole army of CFD engineers doing that. But we are not there. I mean, if that gives you an overall idea and extra due diligence to your design, that's how you should do it.
Yeah. And that is our time. And I would just say, anybody that has any other questions, Kishor's got his email on there. And I know he loves talking about this sort of thing. So it definitely reach out if you've got any more questions for him. And I think maybe one of the keys to that last one is making sure that the model software that you're using has been tested and is a valid software is probably the key to that.
Of course.
But thank you so much, Kishore, for this. The insights were pretty great, and I think everybody's gained a lot from this. So much appreciated. And we'll sign off there, I think.
My pleasure,
All right.
Kevin. Thank you so much. Stay safe, everyone. Stay safe, and we'll be in touch again.
Thank you so much. Have a great day, everybody.
You too.
All right.
Bye-bye.
Bye.